All right, where were we last time? Nope, not there. You want to do that, iterators? Where were we? Instructions. This is where we were. We were talking about instructions. And we didn't get very far into it. Basically, the whole point was we have an 8-bit wide data bus. And our RAM is byte addressable, which is great and all. But we can get 8 bits out of RAM, put it on the bus, and then we have 8 bits to work with. 8 bits is great when it's data. We can have 0 to 255, 256 unique values. That's great. But when we started talking about the data, like the stuff on the bus not being data, we talked about it being like instructions and how we need a way, we know how the computer did computation by manipulating the control signals. But we had to do that. We want to eliminate our necessity of manipulating the control signals. We want the computer to be able to control its own control signals. So we're going to start writing instructions. And instructions often take operands, right? So I want to add what? Or load something into a register, load what? Output something to the output register, output what, right? So we need to say output something. That's the operator, output, operand, what? The argument, the parameter, whatever you want to call it for our function if you think of the operator as a function. We have 8 bits for both that, and we decided, we talked about how we do 4 and 4. We have 4 bits to specify an operator, which means we have 16 unique operators we could have. And then 4 bits to specify an operand, which means we can specify 16 unique things. Often, spoiler, often we're going to be referencing RAM addresses with the operator. So load what? Load the value from this memory address. Well, we have 16 memory addresses, 4 bits, perfect. And we also talked about how, we talked a little bit about microcodes and how there are often, when we are defining, when we are saying these are the instructions for our system, okay, this is the set of instructions we want. We get to decide, we pick what they are. We know we can do a bunch of things by manipulating the control signals, but what do we want to do? And how do we want to do it? These are questions we get to answer because we're inventing this. I know whenever we're given a computer, it's here. This is what you can do with the computer. That's not what we're doing right now. It's, we have our system, what do we want to do with it? We are at the stage where we get to decide what we can do with it and how we do it. We're inventing the instructions. We can make the instructions as specific as we want. But when you make them very specific, I'm trying to think of an example. Our instructions are going to be very, 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 very low level, which is good. But we want them to have some level of generalization to add, we can do more with one instruction, but we also don't want to make it too much because then we lose generalizability, right? It's a fine dance we have to kind of fit, a happy little medium. Ours is going to be our instructions are going to be very low level. But if you think, what needs to happen to load data into a register? Think about it, right? So if I want to say, think about the steps involved to perform the instruction within the context of our system, I want to load data from some memory address to, consider the instruction of loading data from some memory address into register A. Any of the 16 memory addresses could be used in this example, but let's use 15, right? Because why not? It doesn't really matter. Some load a value into register A from some memory address. In this example, I'm going to use memory address 15. 15 or 1111 or F, depending on what base we're talking. That's what we want to do. So what are the steps involved? Well, I need to first put the memory address into the address register. And that takes a clock cycle because we need a clock pulse to latch anything into a register. Once it's in the register, I can then take the data from the register, the data in the register, on our little itty bitty address bus into the RAM. And then from then, because now we are addressing or indexing, whatever word you want to use, we are specifying a memory address, then we can output it into register A. And in order to latch it into register A, we need another clock pulse. My point is, this load A, very low level, right? Now, I didn't say, I could have made an instruction, put this value in the address register. And that instruction, if that was a whole nice unit of instruction, that would only take one clock pulse. But when am I going to want to do that? I'm usually going to want to do that when doing something bigger. So I combine like load into A. Well, that's a step of loading into A. Do you kind of see my point? I'm making load into A the process of what do I want to load into A? Well, I specify a RAM address. Load into A the value from this address. So I have to put it into the address register. Then from there, I can put it into A. That takes 2 clock pulses. I could make an instruction in our system that just says, put this value in the address register. But the utility of an instruction that low level really isn't there. It has value, but it always needs to be accompanied with something else. Why did we put it in there? Well, to get data out of that address to put into memory address A. So I've made it a little bit more, I've added 2 steps, 2 microcodes. The microcodes being the bit patterns for the control signals to make the instruction load data from this address into register A. It takes 2 steps. I could have made it 2 separate independent steps. Take the value from RAM. I could say, put this value, I could write an instruction that says, put this value into the address register. And then I would need a second instruction to say, take the value from the address, from RAM to A. I only have 16 instructions though. So I need to be very discriminatory on what instructions I put. I have a very limited number, so what are the 16 things do I want to do? Do I really want to have 2 instructions, one for put a value into the address register, when really it's always a part of another instruction in terms of like its utility? I feel like I'm having a hard time explaining this. But do you get my point? Are you sure? No? I have 16 instructions. What could they be? Well, we're going to talk about what they could be in a moment, but I have to be very careful. The instructions would be like put a value into register A, put a value into register B, put a value, like add these values, subtract these values, output a value, output a signed value, store a value. Like we're using up our 16 instructions that we could have pretty quickly. Now, I could have one instruction having the bit pattern like 0, 1, 0, 1. I made that up. It doesn't matter. Whatever it is, it doesn't matter. But some instruction, that 1 doesn't mean 1. I have some instruction that means put a value, some val, into address register. Okay? And then I could have another instruction that says put the value 0, 1, 1, 1. I don't know. Put the value from RAM into A. Okay? That would be 1 instruction, 2 instructions, right? Okay, so now I have 14 left. Okay, cool. But I know I'm going to want one for B. I'm going to want to be able to save A, save B, save A, like store the value from the A register back into RAM somewhere. Output a value, output a signed value, add, subtract. We're going to run out of instructions quickly, so we need to be very careful on what we do. Now, putting a value into the address register is going to be a very common thing that we're going to want to do. But think about the instructions we're going to want to do. We're going to want to load a value into A, load a value into B, save a value from A, save a value from B, put a value into the output register, put a different value in the output. All of those things will, by the way, make use of this instruction. So what I could do is say, no. How about the instruction for getting a value into the A register really is one instruction that does these two things? Now I've eliminated one of the 16 possible instructions that I could use, right? Loading a value into the address register is obviously an important step, but it's so specific. And it's always used in combination with another instruction that we can generalize a little bit to say, okay, load into A. It takes two steps, but we free up room for another instruction. I could try to be like, add these values or something where it loads a value to the address register to RAM and then another value into the B. But suddenly, like, oh, that's a little too. We just have to always play this game of what we're going to make these our instructions. Do we want them to be so specific where we have a lot of control, or do we want to generalize where we don't have as much control but we've got more like flexibility almost with the use of our instruction? That's the idea here. And you'll notice that this is a more abstract version. Load into A. Well, what are the steps of that? There are two steps. And those two steps are called the microcodes. More specifically, that would be the bit patterns for the control signals. Right? The first microcode would be like, okay, output the value from wherever, the 1111, into the address register, clock pulse, and then output RAM, input A, clock pulse. Those would be the two microcodes. I think I show you that here. Exactly. So the first one is address in. So wherever that data is coming from, we don't know. But address in, one microcode, and then RAM out, A in, another microcode. Two steps. Each step takes one clock pulse. This means if the instruction is load the value from some memory address into register A, that instruction actually takes two clock pulses. We get tempted, I think, to think like each clock pulse is an instruction. We could design our system like that, but that's too low level. It's really very difficult. That would be something like put the value into register A. That would be like coding at the microcode level. But we want to combine groups of microcodes to make these nice units of instructions that we want to do. All right? We could take it further that in a high-level programming language, let's say C, right? When you say B equals A plus B, that code that you wrote gets converted into this stuff eventually. But when I'm talking of the instruction of load a value into register A, there would be a lot of crap like that going on for the simplest instruction in C of C equals A plus B. Okay? A simple instruction like that. C equals A plus B. Think about it. Think about how you would connect what we're doing in C here, a stupid instruction like this. What would that mean for a system like the ESAP system? Presumably this would be some memory address, this would be another memory address, this would be another memory. So I would need to get the value from the memory address labeled A, put it into some register, the memory address labeled B, put it into another register, add them together, and then store the result into RAM. There's actually a lot of steps there, right? This was just loading a value into A, so there'd be a lot of these. Now, when you have a language like C, you compile it down to stuff that would run on your system. Now, if you're talking about a language like Python or Java, there's a couple of extra steps in there. You compile the bytecode and it runs on a virtual machine and all that stuff, right? But C is a little bit more, it can get you a little closer to your hardware, which is neat. Anyways, this is even more general. But then, of course, in a high-level language like or Java or C or whatever. You could write functions, which are groups of collections like this, and then suddenly you're realizing, wow, there'd be a lot of like individual little clock pulses to do something as simple as like a function that you wrote to calculate the square root of something, I don't know. Point being, more abstract, easier to use, but at the end of the day, it needs to get translated down to these microcodes, and there's a lot of stuff going on there. All right, anyways. The point I'm making is microcodes, they're a thing. But how many microcodes do we want per our instructions? Well, it really depends. What do we want our instructions to be? Yeah? Yeah. Okay, so these two steps put together achieve the instruction of loading the data from a specific RAM address into register A. The steps, individual steps, oh, I need to fix that. The steps, individual steps are called microcodes. These individual steps are called microcodes. Each of these microcodes takes one clock cycle. These instructions would be like, yeah, anyways. Thus, individual instructions may take multiple clock cycles. Any questions about that? Yes? The advantage would be you'd really have to stretch, but we could play the game of do we want, like if we were to allow one microcode for each instruction, what can we do? If we said 2 microcodes for each instruction, what about 3? We could do even more if we allowed 3 microcodes per instruction, like 3 clock pulses. 4, we could do even more. Like there's more we can do. But it's always that game of like, how precise and specific do you want it versus how many instructions do you want to have at your fingertips versus like ease of use and abstraction. It's always a trade-off. So the advantage is you have complete control over your system if you are programming it at individual microcode level. You really do have complete control over everything. But do we need it? Maybe you do. Ours, we're going to make it so it's 2 microcodes. Really, it's going to be 4, but you'll see that it's 2, kind of. We're going to have 2. Each instruction that we have can take up to 2 microcodes, which is, with 2, you could do a lot more. But of course, there's still limitations. But it's still low enough level that you have like complete control over your system. Like the story goes, has anyone heard of the game Roller Coaster Tycoon? Yeah. So like the story goes, like that was a great game. But like that game was really like ahead of its time, and a lot of it was because like a lot of it was written in assembly. And when it was written in like very low level programming, very close to this, okay? Very close to this. But with that control, now there's a little bit of a history here. When you have more control over your system, you can squeeze all of the like power out of the system. You can make it as efficient as possible. It's wild, right? And because of that, this game could run really well for its time. Like it was like ahead of its time, really, because there was a lot of crap going on. Because it was loaded, it was designed so close to the hardware that it could squeeze out every like ounce of power out of your computer to run it nicely. Where if you have a higher level language where it's turning stuff like this automatically into things like that, you as a human might be able to do a little bit more, okay? So by being a little closer to the hardware, you have more control and maybe you could squeeze a little bit more power. Now, at the time Roller Coaster Tycoon came out, that was actually around the time where like the compilers and other types of programming languages were coming out such that it would be very difficult for a human to outcompete a compiler in its ability to make good low-level stuff like this. So the automated tools were getting so good that they were outperforming humans. So that was kind of like the cross point. Today, if you're like, I'm going to program in assembly because I can do better than the C compiler. No, no, you can't. That's not going to happen. It ain't going to happen. And especially if you have these languages like Java, where you have these like just-in-time compilers and all this fancy stuff, where your compiler converts it to code really specifically designed for like all these nuances about your specific hardware and all this stuff, like you're not going to outcompete anymore. But at the time, it was still kind of true. So there is some value programming in such a low level in theory. But really the value is like, well, you have complete control over what's happening on your hardware. You had your hand up? No? Okay, you're good. So does that kind of answer your question? Does it matter? That's up to us. It's where do we want to cut it off? Like abstraction, specificity, number of instructions, you know, it's all kind of like how much control do we need? One clock pulse, that amount of control, like one microcode, it's great and all, but kind of not that necessary. It's a little overkill. 2, still very low. It's the closest to 1 you can be. You can't have 1.5 clock pulses. Kind of. But it's as close to 1 as you can be, but with 2 it's just far more, and you reduce the number of instructions. Oh, it's so nice. So it's really good. All right, okay. So was this clear, right? So the data, I mean, who knows? It doesn't really matter where this data came from, right? This would be like the operand, okay? Load the value. We have some instruction, a 4-bit pattern to mean load. Maybe it's, oh, I got rid of it. 0, 1, 1, 1, whatever, I don't know. It doesn't matter what the code is, the opcode for the instruction. It doesn't matter right now. But it means load a value into register A. Load a value from memory address, whatever, into register A. So what value? This value. It comes from the data bus, goes in the address register. Then, from that address, from RAM, clock pulse. Those are the 2 steps. Clear? So that's how the data would have to be moved around. And there would be the corresponding control logic. Data into the address register, and then data from RAM to A. Yeah? Those are the microcodes. So the bit pattern would be, depending on the order of these things, right? The order of this is kind of arbitrary. Remember, I like the order of my control logic was really for the design. But basically, everything would be 0 except the address control logic. So that's like how we'd set it. And then here, everything would be 0 except for RAM out and A in. Any questions? Other questions? It was a good question. Good question. I think a lot of these things will become more clear once we start talking about the specific instructions that we might want and then how we implement those things. All right, fetch and the instruction register. Okay, so RAM stores both instructions and data. So continuing this idea from above, the example, I want to load data from RAM to register A. The control logic, we did talk a little bit about the control logic above, right? Like what would those signals need to be in that table? The instruction that tells the system this is what the control logic needs to be, in this order, needs to come from somewhere. It comes from RAM. It's in RAM. Okay? So, maybe in RAM, I say like, address 0, I have some 0101. Well, it doesn't matter what it is, okay? And then I'm going 1111, right? And you remember this was kind of like the operator operand, okay? And then in F, I've got, I don't know, 011011111. 1, 2, 3, 4, 5, 6. Look at that, perfect. That's just some data. You can't see that. Can you see that? Now can you see? Perfect. So this is all RAM. This is in RAM though. I've got instructions and data in RAM. This right here, as far as I'm concerned, is the number, whatever that is. this up here, I mean, you could look at this and be like, that's just a number. But I go, no, 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 no. It's all about the meaning of that data, or the meaning of that information. This is an instruction. That means, again, what this pattern is doesn't matter. In fact, I'm pretty sure this is the one I actually used there. This means, we haven't really talked about it yet, but this would mean like, oh, load the value from here into register A. That's what that means. So this is in RAM. I would program this stuff into RAM. Now, you might remember way at the beginning of the semester, I talked about the Harvard architecture and the von Neumann architecture. Who remembers what I said that? It's fine if you don't, because it was a while ago. The design, the overall high-level design of these systems, there are several we can have. And there's two big ones. Really, there's one really, really big one. It's the one that, in general, high level, there's nuance to it, that all of our systems here use. That it's the von Neumann architecture, where you have data and instructions share the same memory space. Okay? Now, we go out of our way to kind of like try to logically separate them, but at the end of the day, it's still in the same chunk of RAM. The Harvard architecture has separate, okay, where you have a RAM for instructions and RAM for data, entirely separate. There are pros and cons to both. We could design our system quite easily to work like that, but we're going to use the von Neumann. There's pros and cons to both. One of the cons of the von Neumann is, well, we'll see. It's kind of fun. But anyways, you might be able to kind of start to think, well, you know, anyways, we'll see as we go. But the point is, we have this, all right? Now, we just talked for a moment. Oh, I need to get this into, if this means load information into register A, information from where? Here. Well, this 1111 had to go to the address register. This is in RAM. Okay, so somehow I need to like get this instruction, decode what it means, and then move the operand where it needs to go. All right? So, okay. Continue from above, although instructions stored in RAM. Yes, so instructions are stored in RAM. And in our design, the RAM address where the instructions start for our system will be address 0. Makes sense, start at the beginning. So a program counter starts at address 0. So the program counter goes, okay, we start at 0. And if I want to start running a program, remember the program counter, we want to keep track of the next instruction to run. So the value in the program counter, which here starts at 0, will be the address of the next instruction to run, which if it's the first one, it's 0. Then the program counter increments, and then it would go down to 1, and then whatever instructions in here, the program counter would say, well, that would be the next instruction we need to run. Okay? So to get the next instruction, we need to get information from the program counter, which stores which instruction do we run next, and have it go into the address register, address 0 in this case. And we need to get the instruction from that address, address 0, and then decode it. Is that clear? Okay? We want to start here. How do we know where to start? Program counter knows where to start. So get the information from the program counter, put it into the address register so we can index RAM at that address. Now, obviously, we're in a bit of a pickle here because, well, the address register is referencing this. But we need it to later, in order to load information to RAM, we needed to reference this value. So we got a little bit of juggling to do. Now, the program counter will become 1. After we run this instruction, we want the program counter to be 1. So it needs to get incremented. So we can always, like, even if the address register is referencing this at a later point in time to get the data from here out to the A register, when it comes time to run the next instruction, we just go, okay, program counter, tell me where to go next. So we can override the contents of the address register whenever we want. But the point is, address register is 0 for like, before I can do anything, it needs to be the address of the instruction to run. And then later, in this loading example, it needs to be the address of the data that I want to get. So we've got some juggling to do. Is this peculiarity? It's not a problem. It's just something we have to be aware of. Is it clear? Okay. Let me open up. There. So what I mean is, I have to get a value from here, put into the address register, 0 for the first instruction, the 0th instruction. And then I would output the instruction from RAM to the bus to go put it somewhere to do its thing. If the instruction is load data from some memory address, we need to get that memory address back into the address register, overwrite the fact that it was referencing address 0 with 1111, so we can output the data from the specified RAM address. When it comes time to do the next instruction, the program counter should be 1, so we output the information from the program counter into the address register, overriding the F or 1111 to get the next instruction, which gets output from RAM, and so on. So the address register is jumping all over the place, and that's by design. So, okay. Then can be out from, okay, so thus to get the next instruction from RAM, the value from the program counter must be sent to the address register, then it can be output from RAM to the bus. However, as previously discussed, the data on the bus is transient, right? Like always before. Like when it came to the output register or the address register. If I want to put something on the output register and I just output the data on the bus, well, the value of the data on the bus is always changing. So the output register would always be jumping around. So if I want to isolate some data from the bus, what do? I put it into a register. I want to isolate the instruction from the bus because I need the bus to put this information back into RAM and then move information from RAM to the A register. I need the bus clear. So I need to take the instruction and put it somewhere so I can interpret what it means and send the operand where it needs to go based on what it means. So we create another register, the instruction register. So yeah, the bus needs to be free to transmit data around the system when performing the instruction, right? As we saw up here, the bus needs to have this value on it, and then later the bus needs to have the data from here on it. So I can't very well have the whole instruction on the bus while also using the bus to move data around. So I need to get the instruction and put it somewhere. And this is perfect because I need to also have the instruction somewhere so I can interpret what it means. So I have an instruction register. I have a register. I'm going to put the instruction containing the operand and the operator and operand for decoding purposes. So it's isolated from the bus, and now I have it, and I can be like, okay, what does this mean? Oh, this means put this value, the operand, into RAM, and then put the information from RAM to the A register. Like that's how it will go. So therefore, a new register created the instruction register. This instruction register will store the instruction for the duration of the execution of that instruction, of its execution on the system. The instruction from RAM must be moved to the instruction register. So we're creating a new register. Great, another register. So the first step we have to do for any instruction is get it from RAM and put it in the instruction register. Before I can even execute an instruction, I got to get it, right? So finally, the program counter needs to be incremented. Okay, so here's what I'm saying. The first instruction from RAM, that's the instruction, yes. Okay. So right here, what does this say? This says, I hit run on my system. The first instruction that I want my computer to run, it needs to know what it is. It's in RAM. So how do I get that so I can start interpreting it? Well, first, what do I got to do? I output from the program counter, 0. first time I hit run. And put into the A register, or the address register, pardon me. The address register now stores 0. I can now get the information from RAM at address 0 and put it into the instruction register. And I can also increment the program counter at this point in time. Okay? Because the program counter increment doesn't need the bus. Right? So it's safe to use the bus to transmit information from RAM to the instruction register and increment the program counter at the same time. So it becomes 1, ready for the next instruction. I didn't have to increment it here. We did talk about how we maybe could kind of increment it here, but we have that potential case where, like, what if it gets latched before it gets into the, what if it updates before it latches into the address register? There was a potential issue there. It wouldn't really be an issue for us, but there's a potential issue. So we do it here. Okay, so this is what we call the fetch cycle. This is a well-defined term, the fetch cycle. Before any instruction can actually be executed on the system, before I can say, load data from some RAM address into register A, before the system can even start thinking about doing that, it needs the instruction. We need to fetch the instruction from RAM. Program counter out, address in, RAM out, instruction register in, and increment program counter. There, now it's in the instruction register. Now I can interpret it and go, oh, that means put data from some memory address into register A. So before I can even start executing an instruction, I need to get it. And to get it, it takes 2 clock cycles. This fetch cycle is 2 clock pulses in our system. Interesting. So no matter what instruction we're going to do, it doesn't matter what we're going to do, we have to fetch it first. Is that clear? I can't start interpreting an instruction from RAM. I need to get it from RAM into its instruction register in our system before it can be decoded. And this is how we get it there. So really, to do any instruction in our system, it actually takes 4 clock pulses. We got to fetch it, then we can interpret it and do it. Like, oh, load, okay, great. I have it in the instruction register. Now go put the operand back into the A address register and then RAM out to A. So it actually takes 4 clock pulses. Note that incrementing the program counter does not require the data bus, so it's isolated like I was saying. We can increment it here even though other things are happening on the system. They can happen in parallel because they're entirely isolated and can't conflict with each other. If you don't believe me, imagine data is going from here down to some instruction register which doesn't exist in the system yet, but it's going to go right around here, by the way. So the data is going here, it's on the bus is being used, but incrementing the program counter, that's just the counter is internal circuitry. It doesn't need the data bus to do it. So we can do that and in parallel do something over there that's entirely independent. Yeah? Come on. You really, at this stage, I'm begging you. You can't look at me like this. I need to know if you're like, yeah, I got it. Or if you're just like, like if I'm explaining something and you don't know it, just go like this. Be like frown or something so I know. What's up?
So the fetch cycle is like instruction, put the first instruction into the instruction register.
It's, yes, but I'm going to modify what you said. The fetch cycle is the first instruction of every instruction. Not just the first, it's not the first instruction of the first instruction. No matter what, if I had another instruction here, I need to fetch it. I need to fetch it, I need to fetch it. No matter what I'm doing, I must fetch. There are a lot of ways we could design our system to do a fetch cycle. We could build some hardware for it. What we're going to do, as we're going to see, is we're going to bake the fetch cycle into every instruction that we're going to do. So every instruction, actually, the first 2 parts of every instruction is going to be a fetch cycle. We don't need to design it like that, but for simplicity, we are going to. But more on that, not right now. So ultimately, the fetch cycle is the first part of any instruction. So all instructions must be fetched from RAM and put into the instruction register. There's actually a funny nuance about like which instruction's fetch cycle was actually running the next instruction, but we'll cross that bridge in a moment. So ultimately, yeah, the fetch cycle is the first part of every instruction. So here's our instruction register. It's going to look like a lot of the other registers, but it's almost like, maybe simpler isn't the right word, but here's the idea. A clock, some stand-in data bus. We have a register. I labeled it instruction because it's the instruction register. We have instruction in, instruction out. However, you will notice that the data in is the full 8 bits from the data bus. But you'll notice that based on this design, I am saying, okay, take all 8 bits, split it, but only take the bottom 4, merge it with 0, so pad it with 0, and then output that to the data bus. If you're looking at that going like, what? What that means is, if I ever put information, if this is my, to be clear, it doesn't actually matter that I do this based on our design of our system, but I believe in like intentionality. Design your system such that like what you mean is a little bit more clear in your design. What that would mean is if this is the whole thing I put in the instruction register, the only thing I ever want to put out back to the data bus is this part. So I basically say output that to the data bus. 0, 0, 0, 0, whatever the operand is. This would be the operand. This is what I want to put back onto the bus to put into the address register to reference the data that I want to load into register A. Now the reason why padding it with 0 isn't necessary is if you go and you look at like the address register. Actually, it kind of is necessary based on one of the instructions we do, but you might say when you load information from the address register to the address register from the bus, you only ever look at the bottom 4 bits, so what do I care is up here? Don't worry about that. It doesn't matter. This design is actually important for our system, but if you thought like, is that needed? Well, there's nuance to it. But here's the instruction register. We can put information in. We can get information out, but we only ever really want the bottom 4 least significant bits to come out of the address or the instruction register. So we can go move around our system however we want. Cool. So, yeah. Above is a configuration of the instruction register. Consider the example in the previous section of loading data from RAM to the register A. The 8 bits instruction is X, 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 Y, 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 Y. 4 and 4. The 4 bits, this, whatever it is, that's the instruction. That's the operator. And the Y, 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 that's the operand. In this case, it specifies the RAM address I want to load data from. This is like a variable. So like in the above example, we used 15. But this is the information I got to output from the instruction register and put into the address register. So that's why it needs to go back to the bus. In other words, the value of these lower 4 bits must be able to be put back onto the main bus. This allows the system to move the variable data operand between the different modules and be manipulated. The values of the most significant 4 bits will remain in the instruction register for processing in some way. So here's now the design. We added the instruction register. If we go back up here, right, with this example, I said, oh, this data 1111 comes from the data bus into here. And then well, where does 1111 come from? Here. So think about the fetch cycle. What would happen? Program counter, address register, RAM to the instruction register. Fetch cycle is done. Now let's finish that load into register A. Operand, least significant 4 bits out. Address register in. RAM out. A in. Those are the four clock cycles, including the fetch and then what actually matters for that specific instruction. program counter address, RAM out instruction, and I guess counter enable. Instruction here, the operand, here, here. Those 4 microcodes, 2 for the fetch and 2 for like what actually has to happen for load A. There we go. Cool? Now, obviously the question remains, okay, so what? How does this, I keep saying the system, oh, the instruction, the most significant 4 bits remain in the instruction register for processing. Well, that processing is what tells the system, okay, microcode 1, microcode 2, microcode 3, microcode 4, or microcode 0, 1, 2, 3 for the instruction. Fetch, fetch, load part 1, load part 2. So somehow we have to get that instruction XXXX that's currently stored in the instruction register. I need to take that value. In fact, actually, it's right here because we split the bottom 4, top 4. So there's an instruction hanging out right here that somehow needs to tell the system, do these 4 microcode steps. And then you've done load A. And also we need to consider, okay, how do we process, like how does the system process it? But what other instructions do we want? We can have 16 instructions. What do we want to do? So that's where we currently are. I'm telling you, this part, once we start talking about the instructions, it's a bit of a jump. I don't think it's like a logical learning curve of like this or anything. No. I think it's like that. But there is some amount, it's small. That's the joke I'm making, right? Like it's itty bitty, all right? But it does, like this is definitely a bit of a jump. Like this is one of the more complex things that we're going to be dealing with is an instruction. What does it mean and how does the system process that instruction? How does it know that 0001 means load A? Which of course we know means those 4 microcodes, 2 for fetch and 2 for the actual like loading A. So this is the type of thing that we need to still cover. And we're going to cover that starting Thursday, I guess. But yeah. Clear? Questions, thoughts, concerns, anything? Happy, sad? I think these are one of those topics where it kind of requires us to jump into the deep end, and then later I throw you the information so you can start to save yourself. Because it does require kind of like a big picture idea before it kind of comes together, for better or worse. All right, cool. I'll see you all later.